All right, so good morning, good afternoon, and good evening, everyone. Welcome back to the point distribution webinar. Today we have Doug Hardin from the Vanderbilt University talking about asymptotics of periodic minimal energy problems. Doug?
Okay, well, thank you very much for the invitation. And yeah, I'm also tired of Zoom, so thanks for putting up with, as I'm sure many of you are as well. And okay, let me go ahead and get, okay, great. I'm not sure, there we go. Yeah, great. Okay, some of this is, because I just didn't know who would be here, is for those of us in this community is kind of standard, but I wanted to set the notation. So anyway, for us, A is going, first of all, I'm going to start out in the non-periodic setting and then try to discuss what happens when we go to periodic configurations. Okay, so we start with a compact set A. For example, A might be the unit sphere in Rn. We have an endpoint configuration, so endpoints in the set A. The F energy is going to be a sum, since often the potential small f may blow up when you plug in 0. So when an xi is equal to xj, there may be a problem. We'll drop the term where I is equal to j and then sum over all the other pairs. In particular, most of our work has concentrated on inverse power laws, or the Rees S potential for S positive. As S goes to 0, then of course this approaches the constant 1 for all x not 0. However, the term that's linear in S is going to be the log of 1 over the modulus of x. So in that case, as S goes to 0, the relevant energy problem becomes the logarithmic kernel. Another kernel that, or potential that will be important for this talk and for us is the Gaussian potential. And we'll see that this plays an important role in the notion of universal optimality. And then the minimal energy problem, I guess I butchered this end part, is to, we want to minimize this energy. And then our job is to find or describe configurations that achieve this minimum energy. Okay, and so that's our job. To set a little, because we're going to see asymptotics of optimal configurations come through here. To set the stage, we're going to use, we're going to note that on the circle, optimal configurations are equally spaced, or equally spaced configurations are optimal. So sorry, I've got to quit Skype. There we go. Are optimal for a large class of potentials, including Rees, Gaussian, others. And that for S, in particular for S not equal to 1 and positive, we have this, that the minimal energy includes a term that's n squared, includes a term that's n to the 1 plus s, and then the corrections are of order n to the s minus 1. And, and in fact, if you want to see complete asymptotic expansion, this is a paper with Johann Brauchart and Ed. And this expansion gives the two dominant terms when S is between 0 and 2. Is that right? No, 3, when S is between 0 and 3, because both of these terms, 1 plus S and 2, will be larger than the n to the S minus 1 until we get to 3. And then the n squared becomes smaller order. But we're concentrating on these two terms in this talk. So I wanted to say a little bit about these two terms. The n squared term, we'll see, well, I give a value here, but it's really it's really an integral over the uniform measure on the circle of the Riesz potential. And so this is a macroscopic kind of term that depends on the density of optimal configurations and not really on the microscopic structure. It depends very weakly on the microscopic structure. On the other hand, the n to the 1 plus s term depends exactly on the fact that these are well, in this case, they're exactly equally spaced. But in the tangent, if you take a look at this in a tangent line to the circle, then the points will, for very large n, will be approximated by equally spaced points in Euclideans on the line, and that's where the appearance of this zeta function is. So this second term, the n to the 1 plus s term, is definitely related to the local structure. Okay, and just to say a little bit about the difference between these two, I wanted to consider the expected value of the energy of identically distributed points. So if omega n is now a random configuration consisting of n independent samples according to some probability measure mu supported on A, then we'll see that we can compute, okay, so let's first compute the expected value of the random, the F energy of the random configuration. Okay, so omega n is this random n independent samples randomly chosen according to some probability measure mu on A. And this expected value collapses. If you bring the sum out, it looks like it's a complicated integral involving all n of these terms. However, when you bring the sum out and then integrate, then all but two of these terms integrate to 1, and you just get a double integral. And in this case, all of these terms are exactly the same. There are n times n minus 1 of them. And we'll call this integral, this should be I sub f at this point. Sorry, this was a, yeah. So anyway, this is in the case of the Riesz potential, this would be the S, this would be xi minus xj to the absolute value to the minus s. And so anyway, this should be I sub f right there. Now, this will, now this might be infinite. However, when it's finite, then it turns out that minimizing the potential, the expected value, the I sub, so I'm writing this now for the case of the inverse power law, Riesz S equilibrium potential. if we minimize this expected value, then in fact, this gives us the first term for the full minimum energy. So in the case of the Riesz potential, this goes back to very classical results in potential theory from the 30s, roughly in the time, the 1930s, so more than 100 years ago. The minimum energy when S is less than D, two things happen. When S is less than D, there exists some measure mu for which this I S of mu is finite. And for the Riesz S potential, in fact, there is a unique mu sub S that minimizes this integral. And what's a little bit surprising, at least to me, is that the minimum possible energy, the dominant term is the same as the expected value of IID points in this integrable case. So this means that for the n squared term, we don't need the crystal structure or the local structure to get the n squared term. So let me just make sure that's clear, right? So we're saying that the expected value goes like n squared times this average, this thing. So that's the expected value. And that will be exactly the same to order n squared as the dominant term in the minimum energy term. Okay, so the n squared is about getting this optimal density right. It also follows in much more generality than I've got here for general F, that when you have a unique equilibrium measure, that the empirical measures for minimal for minimizers, endpoint minimizers, they themselves also must converge in density or in the weak star sense to this minimizing measure. So anyway, the n squared term is only very loosely telling us about the local structure, but is mostly telling us about the macroscopic density as n goes to infinity of optimal endpoint configurations. Now, a conjecture that we've worked on for a long time, and now finally there's beginning to be some progress that I'll talk about in a few settings, is that for Riesz potentials, when we go from when we're between 0 and D, that the next order term, okay, we know the dominant term is this n squared term, but that the next term is going to be of the form n to the 1 plus s over d times some constant that is independent of the set that we're on. Well, okay, right now I'm not going to say. In this case, it depends in a certain way on the set A that I've got, that I'm not putting in right here. Okay. In the periodic case, we'll find that this CSD is a good constant. Anyway, we're looking for things like that. On the circle, we indeed saw, in that case, D is 1. On the circle, we had an expansion exactly of this form. When S is bigger than or equal to D, then this has been the kind of the main area that Ed and I have worked in with a number of people, including Sergei Borodachov, Alex Vlasiuk. There's a big group. Okay, so in this case, when A is a compact D-rectifiable set with positive D-dimensional Hausdorff measure, and S is bigger than or equal to D, then there are two things. Then first of all, the limiting distribution is necessarily the uniform measure on D. And here, uniform measure on D means the D-dimensional Hausdorff measure restricted to A and then normalized. So this would be on smooth surfaces, this would be normalized surface area measure. Or on a volume, this would be normalized volume. If S is bigger than D, then we can show that now the dominant term is n to the 1 plus S over D, which would be larger than an n squared term. We don't yet know what is next, what might be next. That is going to be tricky for us. In any case, there's this constant CSD that's coming up. And in this case, CSD is independent of A and reflects, well, we'll see what it reflects. The only place that A comes in right now is in the D volume, the HD of the D-dimensional Hausdorff measure of A. There's a relation that there's also asymptotics when S equals D, that for us, the analysis is more delicate. And in this case, the local structure is not quite, okay, so the CSD we'll find reflects for S bigger than D, the local structure. When S equals D, we don't quite have the term yet that's reflecting the local structure, but it is reflecting the local density. Okay, so just to show when we put 4,000 points and then numerically run an optimization algorithm of 4,000 points on this torus, when S, the top two configurations are reflecting the equilibrium measure, and in which case the equilibrium measure is non-uniform. And for S bigger than or equal to 2, so the bottom two guys, we're seeing uniform measure. Now, if you look closely at all, and this is not apparent, but if you look closer at all four of these, look on a microscopic scale, you'll see that almost every point has 6 nearest neighbors that are all nearly equally spaced. So this brings us to lambda periodic energy. And so first of all, what do we mean? So for us, lambda is going to be a lattice, by which and in physics, people would call this a Bravais lattice. What we mean is you take, if you're in RD, you take, and I'm going to do a full rank lattice, you need D linearly independent vectors, and you form all integer linear combinations. So another way to say that is I take an invertible D by D matrix A, whose columns will form our basis. And then you apply that to ZD, and this will give you all integer linear combinations of the columns of A. Now, if our potential decays sufficiently rapidly, and I'm going to be a little loose on what that means, but we'll have several cases where that works, then we'll form the lambda periodic potential generated by F. And I'm going to call it capital F sub lambda of X and it's going to be this lattice sum of f of x plus v. And then, okay, I may have some slides where I put minus v, but since lattice is an even structure, it doesn't matter if I add or subtract. Now, this f, so one way to think about f of lambda of x minus y is the energy that's required to place a unit charge at at a point x in the presence of charges at y plus lambda. Okay, so I'll draw, we'll have a picture of that in just a second. Notice that f is lambda periodic. If we consider endpoint configurations that are interacting through this f lambda, then in one sense we're thinking of infinite lambda periodic configurations. On the other hand, since everything is lambda periodic, it doesn't matter if we restrict to a fundamental domain for the lattice or we take the whole set. So we have endpoints interacting through this lambda periodic configuration. I mean, for example, if we periodize the Rees S potential, then the F sub Fs, then the periodic potential is what we refer to as the Epstein zeta function for the lattice, but it's a Hurwitz Epstein zeta function, okay? If we were to sum over V, if we put in x equals 0 and removed v equals 0 from the sum, then this would be the Epstein zeta function. But these will be translates of that function. Now, in this case, say we started with a configuration of 3 points, and I'm going to call one of them x and one of them y, then the sums that we're looking at will be from x to all of the translates of y. And then, okay, so, right. Now, when S is bigger than D, these sums are, it's elementary to show that these sums converge. It's the multi-dimensional and p-test. And that for S less than or equal to D, such sums diverge. So for the rapid decay case, for S bigger than D, then with Brian Simonak and Ed, we have the analog of the result for D-rectifiable sets in this periodic setting, that indeed the dominant term in the energy as is of the form n to the 1 plus s over d times a constant times a measure. In this case, it's the co-volume, in other words, the d-dimensional volume of omega lambda raised to the s minus d. And there's also a result when s equals d. Again, the dominant term is n squared log n. This is not supposed to be there. Okay, well, I just did, okay, so I guess, yeah, this was a redundant slide, I think. Okay. Anyway, yeah, I think this is the slide I wanted. I should have done. Anyway, if you periodize the, for S bigger than D, we get this thing called the Epstein-Hurwitz zeta function. All right, so yeah. As we've said, the CSD constant reflects the local structure. And it's interesting that if you take a scaled copies of a lattice, then you get an upper bound for CSD that says that for any lattice, the CSD is going to be less than or equal to the Epstein zeta function for the lattice times the covolume. When we pick the equilateral lattice, this is lambda 2. So in this case, you could take V1 to be, say, unit vector 1, 0, and V2 to be 1/2 square root of 3 over 2. And this generates the equilateral triangular lattice, which is for us, well, we'll see. They're important conjectures. Now, if you periodize the Gaussian family, then this forms a family of theta functions. And these are called Epstein, well, we refer to them as Epstein-Hurwitz zeta functions. If x is 0, then you get just a more traditional Epstein theta function, but translating by x gives you the potential felt by adding a charge at x in the presence of charges at y plus lambda. When configuration is optimal for all theta functions, in other words, for all A positive, then the configuration is optimal for a large class of potentials that I'll mention in just a minute. And omega n, we'll say, is a lambda periodic, universally optimal endpoint configuration. I'm going to come back to this and show just a few, because our current work now is on trying to establish certain universally optimal endpoint configurations for certain lattices. But I don't have much to report on that right now, but we'll have a little bit. Okay. So for S less than or equal to D, this is good. The main thing I wanted to mention here, the sum, the periodization, this sum is infinite. So we can't go if you have charges at y plus lambda and put something at some x, then necessarily the energy is infinite. So there are different ways of renormalizing the energy in a way to end up with a finite periodic energy. And one way is the use of what are called convergence factors. And I'd like to say a little bit about this. I may say a little bit about some other ways. So I'm happy to answer more questions about this. But the idea of convergence factor is you have a parameterized family of functions. And here I'm using G sub A as our parameterized family. And in fact, the family, one of the families that we often use is the family of Gaussians. The idea is that you multiply your given potential by that is decaying too slowly by a G sub A, and G sub A needs to be such that this product now does have sufficient decay for any A bigger than 0. So, for example, if you take a Reese potential with S bigger than or equal to 0, so the logarithmic case would work as well. You multiply that by a Gaussian, now the product will decay sufficiently fast for this periodization for these periodic sums to converge. Okay, and what we want is we also want that as we take A to 0, our convergence factor disappears, converges to 1. Okay, so we're going to take a limit. We've got the convergence factor that's accelerating decay sufficiently fast so that for any A positive, we get a finite sum. But as A goes to 0, these sums are going to blow up. Okay, so we can show that, okay, for the Reese potential, there's a bigger class of potentials called G-type potentials that I'm not going to discuss here, but this machinery works for a big class of potentials. And it also works for a big class of convergence factors. And it's usually the case that the exact choice of convergence factor doesn't affect the end result. So anyway, what do? You form, so like any good physicist, if something's going to infinity, you want to subtract off infinity. Okay, so what we do is we establish, and this is really using the machinery of what people in physics will call it Ewald summation, or you're working in the Fourier domain and you've got a zeroth constant coefficient that's blowing up, and you just subtract off the constant coefficient. So anyway, what we establish is that given, okay, so for example, if we take the Reese potential, then we can define a constant C sub A so that even though F sub S A lambda of X is blowing up as A goes to 0, we can subtract off a constant that's independent of X and arrive at a finite limit. Now, I think I removed this from the next slide. Yeah, in fact, when you choose C sub A somewhat carefully, then this limit turns out to be the analytic continuation from S bigger than D of the zeta function to all S not equal to D in the complex plane, where this function will have a pole. So, so this machinery of convergence factors is also intimately related, or gives you one way of also computing the analytic continuation. And so it's not surprising that for many of our results, the analytic continuation comes in. I do want to mention that it's surprising to us, or to me a little bit. We'll see that when S is less than 0, between 0, we can go all the way down to 0 and make this machinery work. Whereas if you try other ways, for example, subtracting off, restricting to say rectangles, and then subtracting off a background charge, which is another way, then the best you can do is go down to D-2. And when you go below that, all hell breaks loose. And so I like this convergence factor machinery, and it seems like a principled way of studying these long-range periodic problems. But okay, that's a time for another talk to do more details. I do want to say our main result is that if you pick a lattice in RD, and I'm going to normalize it so that the co-volume is 1. Otherwise, the co-volume is embedded in some of these formulas. Then we again get an n² term. This coefficient is again just an integral of our periodic potential over the fundamental cell. So this is an integral. This reflects the fact that as n goes to infinity, minimal configurations will be uniformly distributed in omega lambda. That is the equilibrium measure. The Haar measure on the fundamental domain will be the equilibrium measure for this problem. And then there's again, now the n² term is the dominant term here, but the next order correction, the n to the 1 plus s over d, is now reflecting the crystal structure or the local structure. And so this is it's reflecting the local structure of the configurations, and we'll see some of this. Now, surprisingly, about at the same time, I think on arXiv, Mircea and Sylvia Sarfati's, Mircea Petraki and Sylvia Sarfati's paper came out before, but they use other methods that work for now S between D-2 and D that have a related structure. Instead of being on the flat torus, they take a limit as n goes to infinity in the presence of a confining external field. And so there are relations and between these, but we're in also slightly different settings. Okay. And we use different techniques here. And there's a reason that, as I said, you can't, with this analysis, you can't go below D-2. For a while now, Kohn and Kumar have conjectured that in various formulations, you can formulate this notion of universal optimality in various formulations, but that in the dimensions 2, 4, 8, and 24, there are these special lattices that are universally optimal. And for us in 2 dimensions, that would be that the hexagonal lattice is optimal. And I'll say a little bit in the context of endpoint periodic configurations in just a second. Now, the famous and amazing result of the group, Vyazovska and Kohn, Kumar, Miller, Radchenko, in 2020, is that this has been proved in dimensions 8 and 24, that the E8 lattice is optimal in R8 and the Leach lattice is optimal is universally optimal in 24 dimensions. And I do want to mention that universal optimality, one way to formulate it is that configurations are optimal for Gaussian potentials, or in the periodic setting are optimal for theta potentials for all A positive. So I wanted to end with some conjectures and just some mild things. So the universal, one way of formulating the universal optimality from RD, a consequence in the periodic setting is that whenever you take a sublattice of a universally optimal lattice, then you'll necessarily get a universally optimal endpoint periodic configuration. So, for example, if we take the lambda 2 lattice, scale the lattice by 2 and take that sublattice, then you get a 4-point configuration, which would consist of, say, these 4 points that are in the fundamental cell, the origin, and then these 3 points. And then the conjecture is that this 4-point configuration is optimal for all theta functions. Or more generally, for any periodized, completely monotone, any periodization of a completely monotone function of distance squared with sufficient decay. All right. And then for 9, these 9 points are optimal. Okay, we can't prove, but are conjectured to be optimal. If you could show this conjecture, that if you had a sequence, if you could establish the universal optimality of a sequence of endpoint configurations of this form, then that would be sufficient to also imply the universal optimality in RD, or in this case, R2. Here's some other interesting for cardinalities that are not amenable, don't form this, for which you can't find a sublattice. So ones, for example, that aren't of the form m squared plus mn plus n squared, for example, 11, then here are just 2 numerically generated optimal solutions for different theta functions. So here the parameter A is 20, and we get, I'm showing, the big circles are showing the separation radius. So you'll find that there will be some points that some of the circles have to be touching. You can see, in this case, it's an interesting arrangement with kind of floaters in the middle. Okay, I like these configurations. So we're interested both numerically in these, but also we're working on establishing optimality in certain cases. As A goes to infinity, you approach a best packing, and the best, removing 1 point from this I think it's okay, I forget. I don't actually know. I think it's conjecture. I think is it known that this is the best backing? Okay, I forget. removing 1 point is, yeah, okay. I'm sorry. I don't know if it's known that that's a best packing or not. The 11-point best packing. I think it's conjectured though, and it may be known. We do have a few. So Eugen Su in his thesis of I think 2016 showed universal optimality for n equals 3 and n equals 2 for the hexagonal lattice. So that for these two, there's a way of taking the hexagonal lattice and rotating it, and you get this sublattice now. You can fit in, this is a configuration of 3 points. And Eugen established that this is the optimal 3-point lambda 2 periodic configuration. So it's optimal for any theta function. And it's a bit careful analysis of the theta functions and where they have their minimum for this lattice. And in fact, if you remove one of those, you get this honeycomb structure. And the honeycomb structure is the optimal 2-point configuration. In other words, you can either put a point here, or you could equivalently have put a point here and remove this one. So you remove one of the 3, and this is the best, this is the universally optimal 2-point configuration. With Nate Tenpass, a current graduate student, we're working on analogous, but for larger n. I'll end with this slide. This was what I was trying to finish right at the last. Somehow my colors came all out, all up. I'll end with some references. Chapter 10 of our book is about periodic energy and about both short range and long range problems. It includes linear programming bounds for this, and it also includes the asymptotic results that I've discussed. Most of what's in chapter 10 comes from these 2 papers. The first paper is just about periodizing long-range potentials. And the second paper that adds Eugen is about the second order term that for these periodic problems. And then here is the famous paper of Cohn, Kumar, Miller, Radchenko, and Piazowska. And I will stop there. And thank you for your attention.
Let's thank the speaker. All right, so now we have time for questions. Just as a reminder, after questions, there will be tea time for socialization for anyone that wants to stay on. But yeah, any questions for our speaker?
Hi, so I may have a question. Hello?
Yes, go ahead.
Oh, hi, Doug. Very nice talk. Thank you very much. So could you please come back to your main theorem?
Yes.
Yes, here. So I was wondering, you know, this quite famous papers by Salfati and Sandier, and then by Sandier and Betterman, where they proved the existence of a constant times n term for the sphere log energy.
Yes, that would be, yes, go ahead.
quite difficult papers, and I mean, it's not easy at all to get to that. So I was wondering, can you go to that from this theorem or from just results? Like, would this mean an alternative way to prove the result?
We hope, okay, so that was the motivation, in fact, that we were trying to find some place where we could establish such a result. So far, we have not been able to so when you go to embedded sets, it's often the case that you want to take a result like a flat space result and then localize it in patches or in flat patches. I mean, so we played that game for general derectifiable sets for the hypersingular, for S bigger than D. We have not been able to take this particular result and map it to embedded sets. For example, the sphere. And there are subtleties about that mapping that we don't quite understand. And yeah, so that's a great question. And it was originally the motivation. And I do want to also emphasize that what happens if you begin trying to approximate, to renormalize the problem by restricting infinite configurations to a large, say a large ball, and then take the radius of the ball to infinity. When S is less than D minus 1, first of all, boundary effects begin to be really important. And if you do things in a symmetrical way, kind of then you can lower it down to D minus 2. But below D minus 2, then if you take the configuration that's periodic and now restrict it to either a union of these patches or the ball, then as you translate points, they kind of exit one part of the boundary and then come in from the other side. And what happens is that those boundary effects dominate the problem. So as far as we can see, when S is below D minus 2, there's this idea of kind of trying to restrict to bounded sets and then analyzing that and then taking a limit is just we can't make sense. So it's a little surprising, or I don't know. Anyway, but this convergence factor treats every point in the configuration, in the infinite configuration, the same in a symmetrical way. So anyway, yeah, we've not been able to map this, and that it's not quite the natural problem. There's yeah, but we are interested in developing results like this in the embedded case, and that's ongoing work. But we've not been able to map these results to there. Okay, that was a long ramble.
Yeah, thank you very much.
Other questions?
I have a question. Do you have maybe suggestions if to consider minimal risk energy either on the sphere or on periodic settings, which will be order of the set term and the fourth term?
I'm sorry, I didn't. So are you asking about a third term?
Yeah, what do you have maybe suggestions?
That would be really interesting. So two things. For the hypersingular case, we don't, maybe there's an n, we know on the circle there's an n squared term, but we don't know, we don't really have, even for s bigger than d, we don't have a good conjecture for this, for a form of the second term. And for s, for this case, yeah, we don't know. It's really interesting whether what could be the third term, and whether it becomes at some point where, I don't know. I mean, at some point we expect the asymptotics to become kind of number theoretic, but I don't know when that happens. And in the sense of, okay, so as we saw that for some configurations, things nicely arrange themselves. And then when you go to one more, it messes stuff up. Okay. Anyway, we don't know. I don't really have, I would love to have conjectures about next terms and stuff. Okay.
Okay, thank you.
So you mentioned that these convergence factors are the right way to look at next order term because they go all the way down to zero. And
yeah, Alex, I don't know. What I don't know is if there's a principled way. I like the convergence factors, right? Because you're approaching the full problem in a way that treats every point the same kind of thing. And that, but yeah, go ahead. I'm sorry to interrupt.
Yeah, I was just going to ask, so what's the approach that fails at d-2? So what is that average? So what the substance of that approach?
So for example,
what would you do?
If you this is essentially one way of doing the analytic continuation. If you do the trick, the analytic continuation of the Riemann zeta function to 0, 1, one way is to begin subtracting off an integral out to some point and looking at a difference. And then, and in our context, what that is essentially doing is looking at the difference between, for each point, you think of the potential of the point and then minus, say, a uniform charge on a subinterval. So you're kind of smoothing it out to make, you're looking at that difference, okay? And that gets you down to d-1 by essentially what you're doing is every time you've got a point, you subtract off in an interval, then you subtract off kind of a uniform charge on that. It's close to this idea of being a Jellium, okay? And that trick works. It gives you kind of one extra power. And if you do it in a symmetrical way, like whenever you have a point at x, you have another point at minus x, mm-hmm. You restrict to a kind of a, something that's even in that sense, then you get one more power. But that breaks down horribly if you try to go below d-2. And even at d-2, it's really delicate. Okay. And another way that Petracchi and Sarfati approach some of these problems is through PDEs. And but in the periodic case, any case, they only go down to d-2.
Yep.
And the yeah.
Yeah. Thanks.
Other questions for our speaker? I had a question. This is mostly just a curiosity. But so the way that the current problem you're looking at is set up, is that right? So I'm just going to describe it on the plane because the plane is going to be the easiest to talk about. So in R2, right, you take a lattice and basically this lets you tile the whole plane with these quadrilaterals, right?
Yes.
And on each of, and basically your set of endpoints, you take a copy and you put it in each one of these quadrilaterals that tile the plane.
Exactly.
Right. But there are other ways to tile the plane, right? Like you can do this with regular hexagons. Would there be any reason to be interested in doing what you're doing with lattices, where you're tiling with quadrilaterals, but instead do it, do it with the other ways of tiling spaces, where you take a copy of the points and put it at each one of the tiles, and then do the energy by summing over each one of them.
Yeah, I mean that's sounds interesting, but it's not a direction that we've thought about at all.
Okay.
So yeah, that would be very interesting. And it is interesting for us that, so for us, sometimes the periodization lattice disappears. For example, in this case, as n goes to infinity, it's really about these internal interactions. And we get that these two constants, CSD, and then, in the case of S is 0, or the log constant, that these constants don't depend on the periodization lattice. Of course, if you're trying to establish kind of optimality for a particular n and a particular lattice, I should have mentioned that, for example, Oleg Musin has a nice paper on Z2 periodic finite configurations. And so so the way I think about this is that this opens up, so on the sphere, even the 5-point problem on S2 is really interesting. So here I think there's kind of of course, we're mostly interested in working in 2 dimensions on the proving optimality for certain configurations in lambda in the hexagon for the hexagonal lattice. But it opens up kind of for a given lattice, probably, things like Z2 or hexagonal lattice, or for us, what's really important right now is Z cross square root of 3Z. That for particular n and particular lambda, there's a whole problem. And when can you establish optimality?
Okay.
So anyway, the main thing is no, I don't, we've not thought about other types of like Penrose tilings or anything like that.
Okay. Thanks. Any other questions for the speaker? Well, in case anyone's feeling shy, I'll stop the recording.